problem 6.1, we have Huggins has an investment project that is following cash flows in year one, $680, in year two, $810, in year three, $940, and in year four, $1,150. We have to ask ourselves from chapter 6 on, do we have an annuity, same amount each year? And the answer is no, we do not. So we cannot use any of the chapter 6 annuity formulas. We must go back to chapter 5. So they want to know, what is the present value of these cash flows at 10%, then 18%, then 24%? What are these cash flows worth today? Present value means today. Back to chapter 5, present value equals future value divided by 1 plus rate to the time. So I'm going to take each individual cash flow and discount it back to today. Discount it back to today, discount it back to today, and so on. In fact, it's instructive sometimes to draw yourself a timeline. So if we were to draw a timeline for this one, we have time 0 with no dollars, time 1 with $680 coming in at the end of the year, year 2 with $810, year 3 with $940, and year 4 with $1,150. And we want to know, what are these worth today? So we take the first one at 10%, and we take 680 divided by 1.1 to the first. And to bring the 810 back to today, we take 810 divided by 1.1 squared. To bring the third cash flow back, we take 940 divided by 1.1 to the third. And to bring the fourth cash flow back to today, we take 1150 and divide by 1.1 to the fourth. If we do that, we get the following answers at 10%. The 680 is worth $618.18 today. The $810 is worth $669.42. The $940 divided by 1.1 to the third is worth $706.24. And the $1150 divided by 1.1 to the fourth is only worth $785.46. Add those cash flows up and we get $2779.30. We do the same thing at 18%, but in that case we divide by 1.18 to each of their respective powers. And we get a total of 23, 23, 27 for the 4 cash flows. And at 24% we divide by 1.24 to the first, second, third, and fourth. And we get a total series of cash flows at 205,463. Note that as my discount rate goes up from 10 to 18 to 24, my total present value amount of these same cash flows decreases. If we in a world with no discounting, we'd have these cash flows adding up to $3,580. And there are your answers to problem number 1. In problem 6.2, we're given choice between 2 investments. Investment X that paid $4,700 a year for 8 years, or investment Y, which pays $6,700 per year for 5 years. Which is better today at a discount rate of 5% and then a discount rate of 15%. Once again, in chapters 6 through 11, I want to draw timelines of my cash flows. So this one looks like this: nothing put in the bank today, but on December 31st of each year, $4,700, $4,700, $4,700, $4,700, all the way out to year number 8. Do we have an annuity is the question. And are we looking to discount it back to today or compound it out to the future? Those are my questions. So the answer is yes, we do indeed have an annuity, and we are looking to discount it because we see the words present value. That means today. What are these cash flows worth today? Now I could step back to chapter 5 if I wanted to and discount each of these cash flows separately and bring them back to today. I could take 4,700 and divide it by 1.05 to the first, 4,700 divided by 1.05 squared, and so on. 4,700 divided by 1.05 cubed, dot, 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 all the way out here. 4,700 divided by 1.05 to the 8th. There I have the chance of making 9 mistakes. Each one of these I might divide incorrectly, write it down incorrectly, whatever, and then when I sum them all up, I might make a 9th mistake. If I realize it's a perpetuity, or an annuity, I can find the present value today by taking 4,700 times 1 minus 1 over 1.05 to the 8th over 0.05. And there, I might make 1 mistake. So my chances are greater of getting it right if I realize I have an annuity. What are my answers? At 5%, and at 15% and 5%, the $4,700 is worth $30,377.10. And the $4,700 a year at 15% is worth $21,090.41. For investment Y, which is $6,700 a year for 5 years, discounted at 5%, I get $29,007.49. And discounted the $6,700 a year for 5 years, discounted at 15% each time, gives me $22,459.44. So which one do I choose? At 5%, obviously, I take the higher value and I choose X. And at 15%, I take the higher value. In this case, I choose Y. And there are your answers to problem number 2. In problem 6.3, we're given that Cannoneer investment project has the following cash flows: $1,225, $1,345, $1,460, and $1,590 in the 4th year. They want to know what is the future value of these cash flows out here in year number 4. So again, this time we're doing future value. So we're going to use the formula future value equals present value times 1 plus R to the T. If I look at my cash flows on a timeline, I see that I do not have an annuity. I cannot use future value annuity formula, so I must go back to chapter 5, calculate the future value of these cash flows. Now this problem trips up a lot of students, so we want to draw the timeline and show how to compound these values out to the 4th year. First, I'm going to take my $1,225 and see how long that's going to be in the bank. Well, that's going to be $1,225 at 8% times 1.08 to the 3rd power. And that will get me out to the 4th year. The second cash flow, $1,345 times 1.08 squared. It's going to be in the bank 2 years, the end of year 2 to the year 3 to year 4. The $1,460 will be in the bank only 1 year, $1,460 times 1.08 to the 1st power. And this $1,590 comes in the bank December 31st. So we know that it's not in the bank any year, so I'm going to take on this one $1,590 times 1.08 to the 0 power, or 1. If I do the math at 8% for 11%, I'll put in 0.11, and 24%, I'll put in 0.24. I'll do the one case. The 1225 compounded for 3 years at 8% is 1543.15. The 1345 compounded at 8% for 2 years is 1568.81. The 1460 compounded at 8% for 1 year is 1576.80. And the 1590 compounded at 8% for 0 years is just 1590. Add those future values up, I get a total at 8% compounded of 6278.76 is the first answer at 8%. And then at 11%, I do the exact same thing, except I just plug in 1.11 here at the various powers. I get a total compounded out at 11% of 65.43.12. And if I compound my money at 24%, I put 1.24 in there in the various boxes, and I get a total of 78.0409. And there are your answers to problem number 3. In problem 6.4, we have an investment that pays $5,500 a year for 15 years. The required return on this investment is 6%. What is the value of the investment today? So what are we looking for? Present value. If payments continue for 15 years, 40 years, 75 years, and forever. Once again, I draw a timeline. I see on my timeline the same amount being deposited each year at the end of each year on December 31st. 5,500, 5,500, 5,500, 5,500, dot, 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 all the way out to years infinity. I do indeed have an annuity. I can discount each of these back one at a time if I want to. 5,500 over 1.06 to the first, 5,500 over 1.06 squared, and so on, but that will take forever, literally, and it would be very tedious and error prone. So I'm going to use the present value annuity formula, C times 1 minus 1 over 1 plus R to the T, all that over R. So for present value of these cash flows for 15 years, if they go out 15 years, I take C of 5,500, R of 0.06, and T of 15. 5,500 times 1 minus 1 over 1.06 to the 15 over 0.06, and I get a present value today of 53,417.37. At 40 years, if these 5,500s continue on for 40 years, the present value of those cash flows is 82,754 and 63 cents. For 75 years, I get a present value at 6% of 90,507.16. And for 1 million years, if I plug the number 1 million in there for T, that's the closest I can get to infinity. I'm not sure what infinity is, so I put a large number in there, and I get 91,666.67. And if I draw this problem out on a XY axis with present value on the Y axis and time on the X axis, you can see that my curve approaches 91,666.67 asymptotically, but never touches it. There you go, and there's your answer to problem 6.4. In problem 6.5, you go into the bank, and the bank puts up $38,000 today and loans you that amount of money at 5.8% for 15 years. In annuity form, what will the annual cash flow be? So do we have an annuity? Yes, you're going to pay the same amount each year for that loan you're getting today at 5.8%, 15 years. So I'm going to plug in, for PVA, I'm going to plug in $38,000. That's the amount you're getting at the bank today. You're trying to figure out what the constant cash flow amount or what your mortgage payment or loan payment will be. We're using the loan equation, the mortgage equation. This could be the credit card equation, the student loan equation. And in this case, we're trying to find out what is that constant payment under these conditions. C times 1 minus 1 over 1.058 to the 15th power divided by 0.058. I get a constant loan payment amount of $38.61 and 62 cents. Now, how much will I pay in total for all of this loan and for all these payments over 15 years? I will pay $57,924.25 in total for the privilege of getting this $38,000 loan today at 5.8%. There's your answer to 6.5. In problem 6.6, we have a company generating $57,000 in annual revenue savings for 7 years from a new information technology database. What is the discount? The discount rate is 7.8% for this project. What is the present value of these savings that are going to come in every year? Do we have an annuity? We have time 0, we have nothing, but in time 1 we get 57,000. Time 2, 57,000. ... all the way out to year number 7, $57,000 coming in savings. What's present value of these? Again, we can do each one independently if we want to. That will take a while, or we can realize we have an annuity and bring them back to today using the present value annuity formula. Much safer, much easier. So the present value of those savings is 57,000 for C times 1 minus 1 over 1.078 to the 7th power over 0.078, and the total present value of my savings, $298,803.87, and there's your answer to problem 6.6. For problem number 7, we have a very valuable life lesson here. What if I deposit $4,000 a year for 20 years into an account, paying 9.7% interest? How much will I have in 20 years? How much will I have in 40 years? So the question again, we must ask on our timeline, do we have an annuity, 4,000, 4,000, 4,000, 4,000, 4,000, ... 4,000? The answer is yes. And are we discounting these back to today or compounding them out into the future is the question. And if we want to know what they're worth out here in 40 years, 20 years and 40 years, we're compounding out to the future. We want the future value of that annuity. That's C times quantity 1 plus R to the T minus 1, all of that over R. So future value in 20 years, I'll have 4,000 times 1 plus 0.097 to the 20th power minus 1, all of that over 0.097. And in 20 years, I will have gathered $221,439.14. If I save for 40 years, this might be the case where I start saving when I'm 25 years old. This might be the case I start saving when I'm 45 years old to have this sort of money when I'm 65. So if I start when I'm 25 years old, and I've taken a finance class and realized the value of investing early, I put 4,000 in the bank at 1.097 to the 40th minus 1 over 0.097. I have $1,631,984.09. So I ask you, what do you think? Is it better to start saving when you're 25 or when you're 45? And this problem tells you how much you'll have gathered if you put these amounts in the bank each and every year and don't touch it. That's your answer to problem 6.7. In problem 6.8, we're given that you want $50,000 in savings out here in year number 12. Your account pays 6.2% per year compounded annually. How much must you invest each and every year? So my goal is to get $50,000 out here. I want to know, what is that constant C amount I have to pay each and every year for 12 years? So I'm looking out and compounding out into the future. Future value of that annuity is C times 1 plus R to the T minus 1 all of that over R. So my $50,000, what I want in 12 years, equals some constant amount, I'm trying to guess what that X is, times quantity 1 plus 0.062 to the 12th minus 1, all of that over 0.062, and I get a constant deposit amount, or constant amount that I will need to have of 29.42. That's how much I'll need to deposit each and every year at 6.2% to make sure I have my $50,000 out here in year number 12. And there's your answer to problem number 8. In problem number 9, we're given that Dinero Bank loans you $50,000 today for a 5-year loan. You're going to pay it off over 5 years at 7.5%. What is the constant payment amount? We're going to use the loan equation, the mortgage equation, the bank equation. You see any of those words, you know you need to use present value annuity. I'm getting the loan today. Present value is $50,000. What's the constant mortgage amount I need to pay, or loan amount I need to pay back to Dinero Bank? I multiply my C times 1 minus 1 over 1.075 is my interest rate to the 5th power over 0.075. My annual payment will be $12,358.24. And in total, I'm going to pay that for 5 years. So my total payment for this $50,000 loan will be $61,791.18 for the privilege of getting that $50,000 loan today. And there's your answer to problem 6.9. Then problem 6.10, maybe pay the reputable life insurance company pays you $40,000 a year forever. Keyword being forever. Do I have an annuity? 40,000, 40,000, 40,000, 40,000, 40,000 forever? Yes, I do. At 5.1%, what is the present value of this perpetuity today? Present value of perpetuity is C over R. As we learned in this chapter 6, same as present value annuity, it just goes on forever. So it's simply C over R. As T goes to a large number, you're left with C over R. Present value of the perpetuity is $40,000 divided by 0.051, and I get a policy amount of $784,313.73. There's your answer to this perpetuity problem. In problem number 11, we have maybe pay life insurance company policy costing $650,000 for a $40,000 a year perpetuity, or an annuity that goes on forever. What is the interest rate? So present value of perpetuity is equal to C over R. Once again, $650,000 is the value of the policy today. The constant annuity amount will be, or perpetuity will be $40,000 divided by R, and for this I get a rate of 6.15%. Here's your answer to problem number 11. In problem number 12, we're going to calculate the EAR, effective annual rate, where we have different compounding periods. Typically the bank is only required to give you the APR, or the stated rate, 7% compounded quarterly. What is the effective annual rate if it's compounded more than once per year? So we're going to look at these four cases. 7% compounded quarterly means I'm going to use an M of 4, and my answer has got to be higher because it's compounded more times per year. Whether you're paying this rate of 7%, you're going to pay more, or receiving 7% compounded quarterly, you're going to receive more. The number is always going to be higher in the EAR column. So the percent EAR is equal to 1 plus that quoted rate over M to the nth power minus 1. In the first case, 1 plus 0.07 to the 1 plus 0.07 over 4 to the 4th power minus 1, I get an answer of 7.1859%. In the second case, 17% compounded monthly, we know it's got to be higher than 17%. 1 plus 0.17 over 12 to the 12th power minus 1, I get 18.3892%. So if I have a credit card that says 17%, but on the back of your credit card bill it says compounded monthly, look for that word compounded. You know you need to calculate the EAR. 13% compounded daily is 1 plus 0.13 over 365 to the 365th power minus 1. It's going to give me 13.8802%. And finally, 10% compounded infinitely. I'm going to put a very large number in here for M, like a million. 1 plus 0.1 over a million to the millionth power minus 1, I get 10.5171. I know my answer's got to be higher because it's compounded more than annually. There are your answers to problem number 12.